Thanks, Bill. Do you have time for questions? Any questions, William? That's because it's for me. It's for me. Go ahead.
I'd like to make a comment. Some time ago, they discovered a meteorite in Antarctica. And the news account said that it was a meteorite that came from Mars. And I was surprised that the comment actually came out, because a simple critical thought would have been, how do you know?
Yeah.
Well, it could be like Mars, well, that's different. But it came from Mars, and it had signs of life on it. And all those things proved to be very questionable, some of them actually false. And I find that in the news, there are often items like that you don't need any numbers, go back at the envelope, calculation. It's just patently phony.
Yeah. Oh, and I find myself sort of routinely, I mean, I have one who sort of tends to eat up newspapers and news and stuff like that, and I find myself frustrated with the lack of integrity in an awful lot of things that are reported.
I was hoping from the sheet that came out, the poster, there was that article, the lines from that the editor about geothermal. I was hoping you might touch on that as well.
Oh, I picked that out that day because I was looking for a hit to sort of, find a particularly outrageous topic to pull as an example. But since I did do that, I looked at there was something that MIT did, which is a much more scholarly approach that they referenced on there. So I actually went into that, and it was about a 400-page scholarly article on geothermal. And, geothermal is evolving, but it still has major challenges, is what I personally expected. I mean, that 15-kilometer one I think is outrageous. I mean, I think that's just completely off the wall. But geothermal, so I read through this article, it's essentially you drill one hole, you drill another hole 800 to 1,000 meters away. You have to use quite sophisticated ways of making, trying to get some penetration between hole number one and hole number two. You inject water down hole number one, go through quite a large area of the earth, at these distances like 5 kilometers underground, and then take the water up the other hole. So these are sort of practical ways of doing geothermal. But if you're using it for actual electricity production as compared to just heating stuff, you look at this, electricity always has this problem that if you want to use it from hot water, for example, there's this efficiency. And the efficiency really is dependent upon the high temperature you can get to from the water compared to the other side of the heat sink. It's basically a thermodynamic problem. Reactors like our CANDU reactors, where you're getting around 300 degrees Celsius at the outlet temperature, and you're heat sinking that to 60 or 70 degrees lower than that, are providing 31 or 32% efficiency. In a coal plant, maybe a little bit more because you can run the higher temperatures. At 5 kilometers, you're typically getting maybe 200 to 220 degrees Celsius, and so the efficiencies of that are probably only about 20–25% in terms of the amount of megawatts that you're actually bringing out of the ground thermally compared to what you're getting in electricity. And as I read through this MIT report, the sort of things that were striking my attention were the items such as borehole instrumentation. I mean, I worked in the 6 years for Schlumberger on oil patch type of tools that have to be used at 2 miles or 3 miles down under the ground. Problems one runs into then is even in an oil well, you're down there at maybe 150 to 200 degrees Celsius at the bottom of a deep oil well. Electronics don't work. I mean, almost all of your electronics that you might want to use, you start getting to the point where they don't work. If you're going much deeper, you're trying to understand the properties of a deep borehole, you have to be able to make some measurements. And so then you've got to figure out ways of actually maybe putting some tool inside of a thermal, like a big thermos for a very short measurement, but continuous downhole measurements of any property is next to impossible because we don't have the technology. And then you get problems with injecting water in here and it goes somewhere else before it comes out here. people who've worked around things like CANDU reactors also know that chemistry of water is brutal. And if you're, one of the big problems, in fact, in oil wells is by the time you're working at, 10,000 feet below the surface of the earth, most water down there is either got salt in it or hydrogen sulfide, and it's very corrosive. And so if you're trying to circulate water down and come back up, the chances of it continuing to bring back some corrosive material, which makes your heat exchangers, tend to last short times, it's probably a very real problem. I don't really know, but I'm guessing that corrosion problems have got to be a real major concern for geothermal. So it's an evolving technology. I think it's a long time before it produces the sort of scale that people would like it to produce.
When storing hydrogen, do you get back energy if you burn it, or
You can use it. I mean, fuel cells make the most sense because fuel cells have very, very good efficiency. You can get 85% or better conversion efficiency from the energy in the hydrogen combining with the oxygen to actual output energy. The stationary fuel cells make a lot of sense. It's just a question, how much. I mean, the hydrogen is looked upon usually as a method for solving some of the transportation issues, and that's why I was looking at the problems of how much hydrogen you actually store on a mobile platform like a car. But in terms of stationary use, hydrogen works very well in terms of putting it through a fuel cell. You can also combust it, but whether you want to do that or not, I'm not sure. I think the efficiency you get from putting through a fuel cell and taking electricity out the other end is probably more useful.
liquid hydrogen really interests me because I read a report from NASA many years ago that said that you have a release of liquid hydrogen in a confined space, you get detonation 100% of the time. And that's not like 99. And so, if you think about a liquid hydrogen fueled passenger train in a tunnel in the mountains,
Yeah.
and it has a bad day, and it detonates, you no longer have a tunnel in the mountains. The gray markers at each end are right off. I don't think.
No, I think
And they want
there are a lot of real practical problems to hydrogen.
liquid hydrogen fueled aircraft are very nice, but I don't know where at the airport they're being fueled.
Yeah.
Certainly not outside the lounge.
No.
Go off to some distant corner behind a wall.
No.
Fuel it over there.
And cryogenic tanks don't weigh nothing. They actually come along.
That's had lots of positive experience.
But trust me, there's an awful lot of room for bright young scientists coming along to work on some of these problems. There'll be a lot of interesting things to solve.
So any other questions? I'd like to call it Krista.
Well, I think this was a very good lecture to end on. Sometimes you get a lecture which deals with more, pure science, the latest in technologies and such, but doesn't really have an application. Sometimes we'll get a lecture which gives a very much applying science to something such as last week's talk by Rosanna Hamsu on energy harvesting. And I found this one very interesting because it didn't take either of those approaches. And so the approach that Bill chose tonight could be applied to just about anything, whether it's pure science or something that's more applied. And as he said, since you're all, the students are very much at the beginning of their careers, this is something that you can use for the rest of your lives. So thank you very much, Bill, on behalf of the people of Science Academy.